In this video, we're going to talk about titration curves, which is a special technique that's used in chemistry to assess the acidity of an unknown solution. And we're going to see what we can learn from those curves. So our learning goals are how to extract useful information from a titration curve. Titration is an analytical technique, and it's used to determine the concentration of acid in a given unknown solution. So the way it works is this. We, for example, might take a strong acid and a strong base. So I'll take nitric acid and sodium hydroxide. And let's say the nitric acid, we don't know what the concentration of that is. So what we do is we're going to add a little bit of sodium hydroxide at a time and measure the pH as a function of how much of the base that we've added. So the reactions that are going on in aqueous solution involve the ions that are created when these two things dissolve in water. They're both strong electrolytes, so the nitric acid forms hydronium ions and nitrate ions. The sodium hydroxide creates sodium ions and hydroxide ions. Now I want to point out that the sodium and the nitrate ions are both spectators in this process. So the net ionic equation that's going on as we're adding base to the nitric acid solution is simply hydronium ion combining with hydroxide ion to make water. And we already know that the equilibrium constant for that is 1 over kW. That's just the reverse of the kW reaction. So it's really high. It's 10 to the 14th. So we can expect that this pretty much goes to completion as it's happening. Now, what does this look like when we plot it out? This is an example of a typical strong acid, strong base titration curve. And you'll notice that it starts at a very low pH, so by looking at where the curve starts with 0 base added, we can tell that it's a very acidic solution. And then it's very flat at the very beginning. In fact, I want to especially point out the shape of this at the beginning and at the point where it turns up. It's very flat at the beginning, which means that as we're adding base, it may be changing the concentration of the acid, but it's not changing it fast enough, I guess, to affect the pH very much. If you think about it, if we reduce the acid by a factor of 2, we would only change the pH by 0.3 units. So as the acid concentration is being reduced, it goes up slightly at first, and it's only when we get very close to the equivalence point that we're now beginning to see a rapid change in pH as we're adding a little bit of base. So that's that sharp upturn that happens. Really what this is it is a vestige of the fact that pH is defined as a logarithmic function. Now the other thing I want to point out here is that the equivalence point occurs right at 7. Okay, that's neutral pH, that's the pH of regular water. And we always get this when we have a strong acid, strong base titration. Now let's shift gears and look at a weak acid titration. What's different about this? Well, the main thing that's different is the acid does not completely dissociate when it dissolves in water. There are undissociated weak acid molecules that are present in the water. So the initial pH is not just going to be the concentration of the weak acid, but it's going to depend upon that concentration, and it's also going to depend upon its equilibrium constant, Ka. So now when we add hydroxide ion, what is it going to do? Well, remember, in most weak acids, there's not a very large concentration of hydronium ion. It's typically on the order of 10 to the minus 3 or even smaller. So when we add the hydroxide, the protons that it mostly sees are the ones that are on the undissociated weak acid. So this is the reaction that's actually happening as we're adding the base. It's stripping protons off of the undissociated weak acid to create its conjugate base, A minus, and water. Now the equilibrium constant for this is going to be the Ka divided by Kw. It's something that you can work out, or it's 1 over the Kb of A minus. And if you look at this reaction, if you were to flip it around, we would have A minus plus H2O goes to Ha plus OH minus, and that is the Kb reaction for the conjugate base. Now since it's 1 over that, and we know that the Kb is going to be a number less than 1, 1 over a number less than 1 is going to be a number that's much greater than 1. So this goes nearly to completion. Now this is what a titration curve would look like if we have a weak acid, and you'll see that qualitatively it's a little different. I've included the red curve, which is the strong acid titration curve, on this, so you can see where they are alike and where they are different. They're mostly different in the region before we get to the equivalence point, and then above the equivalence point they're mostly the same. Now, the way we would actually calculate these points is that we would first solve the equilibrium problem for OH minus, that is the equilibrium that's shown above, OH minus plus HA. We'd then use that value to obtain POH. Remember, we can just take the negative log of that value, or basically negative log 10 of hydroxide ion concentration is POH. We can then use the POH to determine the pH, because the two of them must add up to be 14. Now, in this weak acid titration curve, let's take a look at some of the features that are present here. First of all, you'll notice that the initial pH is higher. I mentioned that to get to that initial pH, it's not just the initial concentration of the acid, but it's also the acid dissociation constant that sets where that pH occurs. The shape of the curve at early stages is also very different. Instead of being flat, it kind of bubbles up a little bit, and that also has to do with the fact that the reaction that's happening is not the direct reaction between hydroxide and hydronium ion, but between hydroxide and undissociated weak acid. You'll note that the equivalence point is above 7. In the strong acid case, it was at 7. Whenever we have a weak acid, we're going to have that pH above 7. And we're going to talk, later on in this module, we're going to talk more about why that occurs. But the shape at the beginning, this characteristic shape, automatically identifies it as a weak acid. So when you see this kind of S shape at the beginning of a titration curve, you probably have a weak acid, not a strong acid. I want to finish by talking about polyprotic acid titration, because that also takes place. And I'm going to show you that curve right off the bat. You'll notice that the first pH is higher even than the weak acid. That's typically true because typically that first weak acid dissociation is a smaller equilibrium constant than it is in just a typical weak acid. The first equivalence point is also going to be higher. It's greater than 7. The shape of the curve is very much like a weak acid titration. You'll also see that there's a staircase profile because we have more than one proton that's being removed. Okay, the base is going to keep removing protons until it can't do that anymore. So the number of steps tells us something about the number of acidic protons that are present in this acid. So we can tell, because there's 2 steps in this case, that this is a diprotic acid. Now I've labeled some other things in this. I mean, mostly I think what I want you to pay attention to is there are 2 equivalence points. One occurs when half of all of the first proton has been removed from the polyprotic acid, and the second was when both of the acidic protons are removed. But there's more to learn about this, and this is really just meant to be an introduction to titration curves.